Okay. Sorry. So can everyone hear me and see me? Yes. Okay. So I will start. Hello, everyone. Thank you for joining. For joining the event. I am Filip Cano. I am a PhD student at the Graz University of Technology. And what I'm presenting you today is our joint work. This is joint work with some colleagues in Graz University of Technology and some colleagues from Yale University about analyzing intentional behaviors in autonomous agents under uncertainty. This is a paper that we presented at AGI last year, and that we are still working on some extensions of this method. So the motivation that we had starting this work is that autonomous agents are becoming more and more influential and deployed in many more places in our lives, and in particular in places that they should be that there could be some safety critical issues, and if an agent causes some harm, we should have a way to hold it accountable, so that as a society we can trust that these possible harms don't get unpunished. But it is different from a human. If you can think of, it's different level of responsibility if you cause a harm accidentally, if you neglected some safety measures and that directly went to causing some harm, or if you do it intentionally. And we should hold autonomous agents to a similar standard. But we have the issue that it's really difficult to say what does it mean that an agent can cause a harm intentionally, and this is what we try to model in this work. So what we propose is a method to analyze what we call evidence of intentional behavior. So we cannot kind of go into the mind of the autonomous agent. That's why we always talk about evidence and not directly like intentional behavior. Because we are considering machine learning based models. So in this type of belief, desire, intention models, this would be easy, but in the agents that are used currently today, current reinforcement learning uses neural networks, and there is not a clear way to say what is kind of going inside the agent's mind. We use the tool of counterfactual reasoning. This is widely used in interpretability of machine learning. Basically, we consider a factual sequence of events that kind of actually happened, and we ask counterfactual questions of two types. We ask questions of the type of what could the agent have done differently along this factual trace of events, and what would the agent have done in different situations. So if the situation was slightly different, what would the agent have done? From the technical point, we model our problem as a Markov decision process. I'm assuming that many of you may not be really familiar with the Markov decision process, but if the easy way to think of it, or the high-level way to think of it, you have some environment that is modeled with this. This is a probabilistic model, and you have an agent that makes actions, and these actions affect the environment. And the whole Markovian side is that there are some probabilities. So actions can have different effects, depend on, and this is how we model like probabilistic behavior of our environment. We model our agent as a policy in the MDP that decides the actions to take. And what we say is that there are certain states that are, for example, considered harmful states, that we want to check whether the agent had intention to reach them. And this is the set of states that is of interest for us. Why did we choose MDPs? Well, they are standard formalization of reinforcement learning, and reinforcement learning is widely used for this type of autonomous agents. And also there are great tools available from the site. maybe I come more from a side of formal verification, formal methods, and there are many tools available to study properties of Markov decision processes. So the main concept that we want to introduce is what we call this agency and intention quotient. So let me paint you an idea. You have a trace that is marked here in the Markov decision process, and in the top side you see that the trace. There are different agents that can go through this trace, and these different agents would have a certain probability of reaching a certain state. We would have the probability max. This would be the agent that maximizes going to the purple states. We would have this minimizer that minimizes this going to these purple states, and then we would have the agent itself, the agent that we are interested in, that we want to hold accountable. So at every state, there are two measures that are of interest for us. One is the gap between the minimum and the maximum. This is what we call agency, because this gives an idea of what effect can the actions of the agent have on the outcomes of the environment. So you would see here in the left side, there is a high agency, and on the right side, there is less amount of agency. And the other point that we consider is where does the agent lie between the minimizer and the maximizer? So we consider that the minimizer is 0 and the maximizer is 1. Where does the agent between 0 and 1 lie there? This gives an idea of how much the agent is pushing for maximizing the probability of reaching these bad states, or pushing for minimizing the probability. This is for a single state, and then for a trace, we make the weighted average of this, and we weight precisely by the agency. So the states that the agent can affect the outcomes the most are the ones that are considered more important. And this answers the question of this is our way to ask the question of what could the agent have done differently, because we are considering any other type of agent that lies between this min and the max, and what could the agent have done different in the same trace. To give you an example, imagine you have a car that is driving. There is a truck here, and this is supposed to be a pedestrian, and the car tries to the car maybe collides with the pedestrian, and we could ask, was this hit intentional, or could the hit have been prevented? And we would compute this, and we have a tool to automatically compute these graphs. And if we get a graph like this, it kind of says that, okay, the agent is really close to the minimizer, which kind of gives an idea that this was more often, or gives more evidence that there is an accidental hit there. And maybe if you consider a more complicated example, what if there is some kind of puddle of water or ice, and that makes the car that makes the agent have less control of the car because the floor is more slippery, something like that. In such a case, then the graphs would be very close together, and that really gives us no much information of what is the agent trying to do, for example. And in these cases, we say that we don't have enough evidence, and what we will do is to ask for different types of environments. So first, I just want to talk about this. What is enough? So we assume that there is a certain thresholds on the agency and certain thresholds on the intention quotient, and these thresholds are assumed to be application dependent. So once you have an accountability process in mind, you would have to define certain thresholds and then see how the agent lies between these thresholds. So in the case that we have an inconclusive case like this, we would say that we have to produce more traces, and these more traces produce more evidence. This is asking what in different situations. So if the traces is like different, if the conditions are different, if instead of if instead of raining it's sunny, if instead of a truck in front of you there is a tree that's hiding the car, this type of changes in the environment then change the possible outcomes, and we want to test the same agent what would have done in these different outcomes. And with this, we propose a whole loop system in which we would check the original trace, check if there is enough evidence. If there is enough evidence, we would be happy, and we would go to see if the agent quotient is on the intentional threshold, on the unintentional, or if there is not enough evidence. And in case that there is not enough evidence, what we propose is to generate counterfactual traces in an automated way, aggregate the results, and then ask the question again. And of course, this can be repeated if the test is inconclusive. This can be repeated many times, and at some point there is some stopping mechanism that would say, okay, whatever we found, we cannot really without a reasonable doubt assume that this was intentional, and depending on the application, the threshold would be the one that is deciding what consequences or what kind of legal consequences the action has. But from a technical point of view, we are producing a number between 0 and 1, and then the interpretation of this number is more left to the concrete cases. So we made a case study to show that this is, in fact, can be computed and gets reasonable numbers. We built 3 agents that are one was more prudent and one was more negligent, and the other one was kind of more ill-behaved. And we made the whole computing the counterfactual traces and doing the model checking, and things can be computed for these small examples. Okay, so this finished my presentation. Just to recap, in this work we tried to analyze where there is evidence of intentional behavior from an autonomous agent, and in this case, an autonomous agent, we can think of it as a reinforcement learning agent. We do it with counterfactual analysis, asking what could the agent have done differently and what would an agent have done in a different situation. The concrete modeling that we use is the Markov decision process, because then we can use model checking tools. And this is my website if you want to check more details of the work, or if you want to contact me for any research questions or collaborations. Thank you very much. Okay. I'm sorry, because I don't know now if there are questions or...
Thanks, Philip. So if there are any questions, you can go over to your lounge, over to the lounge section where we have dedicated a table for you. So if any of the attendees have any questions, you can answer them there. And thank you for your presentation. It was wonderful and got some very good insights from that. So thank you for that.
Thank you very much, the organization.
Zenlong, yeah, I will just add him to the stage. Just give me 1 second.
All right. Can you hear me and see me? Okay, let me share my screen. Tab window. Okay, I'm going to share my entire screen, and I don't know how to make it share. All right. So can everyone see me and hear me, right? Okay. So let me see. I cannot see the other places. Let me see what happened to this one. Give me a second to share. This time I'm going to directly open my PowerPoint. Okay, I think. All right, I'll just share my entire screen. I think that's the only way. Okay. Okay, hello everyone. Thank you for joining this session. And I am the associate professor from Department of Geography at Pennsylvania State University. And today I'm going to share one of our research work titled Autonomous GIS, the next generation AI-powered GIS. This work is done with my student Huan Ying here, and we have a paper published in the Journal of Digital Earth. All right, so I guess some of the audience might do not know what is GIS, or at least the more detail of that. So just a quick introduction about GIS. It is a system designed to capture, store, query, analyze, display geospatial data. So it's called geographic information system. I guess probably most of you have heard that before, or maybe some of you use that. And it basically uses the system we can abstract and model the real world into a GIS world, like using layers to represent different kind of data and phenomena, and we can do spatial analysis of that. So spatial analysis here is a core component of GIS. And so the basic for the spatial analysis is that it is a process of examining the location, attribute, and relationship of features in spatial data through analytical approaches. It's kind of a data science. We call it spatial data science here. And so geoprocess workflow, which is another term in GIS here, and it's kind of integrate spatial operation tools and also spatial data to produce new data set, maps, charts, and reports. So the point I want to make here is that any spatial analysis actually can be converted or can be considered as geoprocessing workflow, which is we have the input data. You can think input spatial data, and then this data being analyzed or processed by different tools and generate some intermediate data. And finally, we can produce the final output. The output will be the result to answer spatial questions. It can be some new spatial data set, some maps, charts, or reports here. So that's a spatial analysis, which can be treated as geoprocessing workflow. So we're going to go back to this later. And this is an example. I'll just quickly show you that what a geoprocessing workflow looks like. So this workflow is created using ArcGIS model builder to identify the suitable areas for the new school. So this is a typical, site selection problem. There are many other problems that we can think of. Identify a new restaurant, a new factory, for example. And we have this data input on the left side.
One second. Hey Zhenlong, I think there seems to be a problem with your presentation. We are not able to see the slide. Can you fix?
Oh, really?
Yes.
So, oh my God. So that's why I'm not sure what. Let me see. I'm sorry about that.
Yeah, sure.
You cannot see the slides, right? Oh, that's a problem. Let me share screen. Oh yeah, here this time. Yeah, I'm sorry about that. So I'm actually not here. You can hear me, right? You heard me before. So I'm going to start from here. Spatial analysis as a geoprocessing workflow here. So this is a workflow created with ArcGIS model builder and for the site selection, as I said before. So normally we have this kind of workflow built by a GIS expert or a spatial analyst. So you need to have the knowledge or domain knowledge or GIS and also GIS knowledge to build this workflow to answer the problem, answer the question, for example, identify the best location for the school here. And we have, again, input and output here as a map this time. And there are some intermediate, like some steps, some data sets generated in the middle. We treat them as intermediate, data set and also some operation that we use here. So the AI in GIS here, we have that has been a number of studies or different kind of studies here. And in general, we can consider that in 3 categories. So in GIS, we can use AI as information extractor. For example, we can extract some useful information from tweets, for example, and extract sidewalk from street view imageries, and many other studies to extract relative information from using the AI, like extract flood water depths from photos, for example. And the AI can also be used as a spatial model to predict, for example, the air quality for weather forecasting. And I'll have some list some examples here. And finally, AI can be used as a GIS agent. So this is a topic that we're talking about here in my talk. Is we call it autonomous GIS. Actually, it's just it's kind of a GIS agent. We use AI, use LLM here as a brain, as a reasoning core to achieve the goal here. So the definition of autonomous GIS here, we define this autonomous GIS as AI-powered GIS. We basically leverage or use the LLM's general abilities in reasoning, which is natural language understanding, reasoning, coding, to address spatial problem. So the key here is that to address this problem automatically without or with very minimum human interaction. And the key is to build a dual processing workflow, as I showed you before, and also run the workflow in an automatic way. And this workflow, normally in the traditional GIS, we need to have an expert like spatial analyst to build this. But now we are trying to see whether we can have the AI, like the LLM, to build that for us, and also create the code and run finally the final program to solve the spatial problem. And we envisioned 5 autonomous goals here. There is we call it self-generating, which generates the dual processing workflow by itself, self-organizing, growing, and verifying. Also, this is kind of code debug or review and test. Finally, it can self-executing, which is run the workflow, for example, to produce the final output. So, and this is a prototype of the autonomous GIS that we kind of develop here, use to demonstrate, how the system will work. It looks like, and we call it LMGeo here. So you can see this is the overall workflow here. We start with spatial problem that you can ask using natural language to the system, and then the system here we are using GPT-4 as the brain. The system will create a workflow. Here is a dual processing workflow, or we call it solution generation stage. And this workflow will include this kind of what kind of data needed, and there are some operations, which is spatial operations, and some data generated based on this workflow, and finally is final result, and which is we call it the final answer here. And then once we have this workflow generated, which is only kind of a solution, which is a plan, a step. We don't have any code, creating now. And next step is to have the GPT here using GPT-4 to create the code, which is for each operation here, it will be a Python function. And then this function will take the input output defined in the workflow to actually implement that task that you can think that's spatial analysis task. Finally, we'll put all this workflow, this function together, and to connect these functions based on the workflow, and finally run this program, and we generate the answer. So this is the overall steps for the LMGeo, which is just the prototype of this system that we envision here. So due to the time limitation, I'm going to quickly show you some example, some case study that we tested in this study. So the first one is we try to count the population, have system count the population living near the hazardous waste, which is we ask the system to find out the total population that lives within each sensor tract that contains some waste facilities. The study area is one state in the U.S., North Carolina, and also generate a map to show the spatial distribution, and also highlight the borders of tracts that have hazardous waste facilities. So those are kind of the spatial problem that you can ask using natural language. And then we give the system, let the system know that we have those data locations. So for now. And then this is the result here. First, it generates this workflow, dual processing workflow by itself directly. And then based on this, each of these, you can see this data input, and there's some data node, spatial operation node, and some intermediate data output. Finally, we have this final output here. So this, based on this workflow, and it will generate the code, which is, you can see this code here. And then finally, to run this workflow, which is run this program, it will produce a result here. First, we have number to the population, and then we have a map here, which is all those are correct based on our verification. The second case is to show the monthly change rate of population mobility for each region in a France map. And this mobility is this time, and the time here is during the COVID period. We want to see that how the COVID has impacted the mobility in France. And we want to create a submap for each month in a map matrix here. And also we want the system to draw a line chart to show the monthly trend rate for all regions. You can think the region is states, and then we tell it that which the x-axis is a month here. So those are requirements and some data locations, which they are all spatial data. And then this is the result here again. It generates this solution graph, which is dual processing workflow, which is, makes sense here. And then based on this workflow, it generates the code, and also this to B and C here is about the result. This is the map, which is each map is for each month showing the mobility reduction rate. We have this legend here, and then this C here is the trend here. We didn't make any change, any modification to this output. It's just it's the direct output from the system. And finally, the third one, just a quick one, draw a map to show a death rate of COVID-19 among these contiguous US counties. So we use we ask it to use the cumulative COVID-19 data to compute death rate, and then some other requirement here. We want a scatter plot to show the correlation of death rate and senior resident rate, and also we want to include R-square and p-value, and some other requirement here for the figures. And then this data location, again, we tell the system where the data is. This is the output again, based on just the research question, the spatial problem. It generates this, I think, very nice workflow, which makes sense here. You can see three data set, and produce two output here, two output with this purple color. And then this is the map. This is the map showing that rate. And this is a scatter plot for based on the requirement. So this is a 3-case study here. We have all that reported in the paper. And then after that, I just want to have a quick mention about the potential forms or formats of this autonomous GIS that we envision. It can be a standalone system, which is a system we are trying to build right now. Have a user interface based on a web-based interface. You can input the question and then create all this workflow code and also result here. And then we also envision that it can be a co-pilot style, like if we can put a chat box into the current state of our GIS, like ArcGIS or the QGIS, which is open source one, and then to leverage or to integrate the existing spatial analysis functions or tools within the system, and it will automatically build a workflow, and then to run this workflow to produce the final result. Which this might be another way to achieve this autonomous GIS, here. And so I do have a quick video demonstration to show you how this works on the fly. Let me see how I can play the code here, the video here. Yeah. This is the video showing the case study 2 here. I'm going to just show you one of the studies here. And you can see this is the system. Now it's only on GitHub. It's on GitHub here. You can input the task just by typing your question here and some data. And then you just run all the code, run all the cells. This is the prompt for the solution generation. And we pre-design some prompt and then to fine-tune it to make sure it's generated the workflow that makes sense. And then this is outputting or generating this dual processing workflow node. We have operation node, data nodes, and also the edges, how these nodes are connected together. So this is the generated workflow. as you can see here, with the data input, output, and also some intermediate data generated and some function that we need to implement. And you can actually drag and drop it to change the shape of this workflow, and it is saved as a file on your disk. Now, once we have this workflow, the system will generate, as I said before, generate the code for each operation, which is for each operation node in the workflow. And for each operation now, we have added the reviewing, which is testing or like code debugging function. It will test whether this function is okay, or if there's any issue, it will try to regenerate. And so you can see this is generating the steps. We have 5 operation nodes, generate one by one. Once we finish this, it will go to the assembly program, which is, I'm sorry. Why it's, oh no. Okay, this is the assembly program code generation now, which now we have generated the functions for each. Oh no, I'm sorry. Well, we have generated functions for each operation node, and now it's trying to put everything together to generate the final program. Now it's running this workflow, which is you can see the entire workflow, which is one, put all the code together. We get an error here, which is something I want to demonstrate. An error occurred. So now the system will automatically send the error back to the system, to the GPT-4, and try to debug it. And then it will regenerate this code one more time. So you can set how many times you want it to try. Here we set 10 times. But let's see the second time, it will regenerate the code based on the error information, still using the same kind of workflow. And we will try the second time. This time, I know that it's success. If you can see the result here, just give it a wait. Yeah, we have this map generated. And also, you will see that the line chart had been generated also. So you are seeing 2 maps. This is just the display issue in the system. And this is the line chart, as I showed you in the slides before. So everything is done automatically. I didn't touch anything when we do the recording. Just we get the first run is get error. Second run, the second try is successfully generated the result. All right. So this is this is the demonstration here. There are some limitations and also a lot of future research that we can work on. I mean, AMGeo is only a prototype, which is still in a very early stage. And we are still working on that to address a lot of limitations and try to add more function here. And I don't have much time to talk about that, but I do list some kind of the current limitations and the future research direction that we as a community can work on here. And to learn more about those, there are more discussions, some more detailed discussions are discussed in this paper, which we published in the International Journal of Digital Earth. And also we have the code open sourced here. We do have already several contributors working together to fix some bugs here. So we welcome you all to try to work together to make this better. And thank you. Okay, I think I'm done. And if you have any questions, feel free to reach out to me and send me an email, and I'm happy to talk with you. Thank you.
Hello, can you hear me? Okay, let me share the screen. Okay. Hello, everyone. My name is Yu Hao from UC Riverside. Today, I will present my research entitled "ENV Prompting Large Language Models to Perform Static Analysis." Perform static analysis by pseudocode execution and verification. So first, let me introduce some background and the related work. So a lot of research has been conducted on the application of large language models in software engineering. For example, the code generation, code summarization, test generation, patch generation, also as well as program analysis, which is somehow more complex and difficult. And however, the hallucination issue in large language model is a big challenge. So typically there would be three kinds of hallucination. The input conflicting hallucination, which means the output of a large language model is inconsistent with user provided input. The second one is the context conflicting hallucination, which means the output of language model is inconsistent with the model's own previously generated output. So the last one means is fact conflicting hallucinations, which means the output is inconsistent with the established real-world knowledge. So our method named E&V, which is the execution and verification, is designed to enhance the capability of LLMs in performing static analysis, as well as mitigate the hallucinations during the analysis. And also, we want to reduce the need of intensive human effort. This figure represents a high-level workflow of the E&V. First, it requires three types of input. So the task information, for example, what kinds of static analysis we want. For example, backward tent analysis or some other kinds of analysis. The second one is the pseudocode, the pseudocode of the static analysis, which are used to guide the LLMs to perform static analysis. And also the execution specifications, which is which is the specification for the pseudocode, which is used to verify the execution of the pseudocode later. And the next one is the source code of the target program to be analyzed. Specifically, the agent here utilizes the pseudocode execution to perform a single step of the static analysis at a time, instead of conducting end-to-end static analysis on all source code, because we know there are token limitation. It's impossible. And then the agent would send the prompt to the pseudocode execution and to prompt to stimulate the execution of the pseudocode. And after obtaining the corresponding response from the LLMs, the analysis results are transferred to a specialized verification component. We call it execution specifications verification. And besides, the source code retrieval component is used to extract the related source code, which is implemented by a traditional static analysis way in order to handle the extensive code base. And the possible other tools can be integrated into the ENV and would help other analysis if necessary. So now I will introduce pseudocode execution. So if we employing LMs for static analysis with straightforward prompt written in natural language, would use some unreliable and sometimes even incorrect results. So to mitigate this, we propose pseudocode execution to enhance the precision and the reliability of the LMs in performing static analysis. There are several advantages. So the first one is more precise prompt. So leveraging well-structured control flow in pseudocode, we can design prompt with less ambiguity. So the LLMs would be prompted to follow the sequence branch loop and the function calls to take different actions. This level of precision is hard to achieve with natural language prompt. especially with the limited token. For example, in this figure, we can see there would be the if condition, then, and also the else if and then some control flow, just like the program language. The second advantage is debugging capability. So it is sometimes very difficult to figure out which part of the prompt are causing the wrong analysis results. By integrating the prompt that make LM to output the execution process step by step, LMs can output the intermediate execution step of the pseudocode for developer to debug the execution and later to refine the pseudocode. Just like the utilize the print statement for debugging in the traditional programming. Yeah. And this debugging capability is highly depends on the control flow graph of the pseudocode. And also we can have automatic verification, which would be introduced later. And we can also have a better task decomposition and a range of application. So now I will introduce the execution specification verification. So as we just see, in fact, there are two results in the pseudocode execution. The first one is the execution process based on the control flow of pseudocode. And the second one is the analysis results based on the goal of the pseudocode. So just like the real code, so if the code is executed, the results of the code will be naturally be generated. So when we prompt LM to stimulate the execution of pseudocode of static analysis, the results of static analysis will also be generated naturally by executing the pseudocode. So the key insight of the verification components is that we can indirectly determine whether the analysis result is wrong or not by verifying the execution of the pseudocode. That means if the execution of pseudocode is wrong, then that means the analysis results must be wrong. So there are three kinds of violation. So the first one is the unrecognized execution. So if the analysis is guided by a pseudocode and produce some explicitly well-defined output, it becomes very critical to predetermine accepted set of the categories for those output, and the differences from those from this predetermined sets are kinds of violation. For example, we can say uh, in the line of the line 7, yeah. So we can print some information called a category. So if we found okay, the output includes some other category, that means there should be a violation of unrecognized acquisition. The second one is the incomplete acquisition. So each analysis would potentially generate multiple outputs. So to determine their completeness, strict verification are required. So if the output is missing any of the specified elements, the output is considered incomplete and therefore violates this specification. So the next one is the inconsistent acquisition. So given that analysis could be produce multiple outputs, so it is important to establish a specification for consistency among all those outputs. And then we apply this method, the EIDV, to a real-world static analysis task. So here, the triaging crash is a software in software is a critical process undertaken by many software providers, which involve identify the root cause of a crash, grouping identical bugs, and assign them to the respective developer responsible for the blamed function. So the state-of-the-art static analysis tool, which called Retracer, performs a backward tent analysis to find the blamed function. So where the patches should be located or nearby those blamed function. By this way, it's offer a Oh, okay. I will. Yeah, so we apply the this method to this task, and we want to evaluate it in a real world static analysis task. And in the evaluation, we choose the GPT-4 32K, and during the pseudocode execution, we set the temperature to 0 to reduce the randomness. And if there are any execution violation, we would increase the temperature by 0.2 and kill the 2.0. And for the dataset, we pick 170 recently fixed KSAM bug in the Linux kernel. And we can say that this table shows the accuracy of our method. We manually evaluated the correctness of these results, and we observe that we achieve an overall accuracy of 81% in identifying the blame function. And also, we further investigated the correct case to understand the effectiveness of our verification process. So we can say for the data ESV, which means the differences between with and without the verification. So our verification components improves the accuracy by 52% from 28% to 81%. Then we then analysis the execution of our prototype for the cracked cases improved by the verification process, which is a data ESV. We can say that there are about 25% execution violation among all the violation of the pseudocode. But this result means not all the execution needs the violation process, but however, any violation would means the results are incorrect. And then this table shows more detail about the violation. So we observe that there are 15% unrecognized execution, and 23% incomplete execution, and 61% inconsistent execution. And this table shows the performance of our prototype. So overall, it's there would be an increase of 46% of the total number of the tokens, and which brings an increase of 52% in accuracy. That's all. Thanks. And you can find me by the Twitter or email.
Hi everyone, I hope you can see my screen, and screen sharing and hear everything. So my name is Brandon Kynock. I'm an undergraduate computer science student at the University of Texas at Austin. And I had the privilege of doing LLM research with Cisco throughout the summer of 2023. And today I'll be discussing Recall-M, an adaptable memory mechanism with temporal understanding for large language models. So long-term memory means that we can interact with LLMs over extended periods and use this long-term memory to recall and reason about knowledge previously provided to the system. So what exactly do I mean by adaptable? This means that the system is very effective at updating beliefs and knowledge previously provided to it. So without further ado, I'm going to jump into the details of the system. And thank you all for attending. I hope you enjoy. I'm going to start out by diving into why we should even bother supplementing LLMs with long-term memory. I'll explain the Recall-M architecture in detail and conclude with our experiments and results. Recall-M is a complete system. It's open source and it's fully implemented. The code is available online at the Cisco Deep Vision GitHub, which is linked below. This is a quick code sample demonstrating how easy it is to use the system in Python. So as you can see, usage is very simple. We begin by importing recall_m and initializing a recall_m object. We can then start performing knowledge updates or question the system in just a single line of code. The GitHub page contains detailed instructions on how to initialize the system and start using recall_m. Now that we have an idea of what recall_m does, why should we bother supplementing LLMs with long-term memory? And the answer is quite simple. We're all very familiar with the remarkable capabilities that LLMs have demonstrated in recent times, and they've drastically changed the way that humans interact with AI systems. Furthermore, LLMs have demonstrated remarkable capabilities across a large variety of tasks and domains. In short, LLMs have brought us one step closer to achieving AGI. However, with the benefit of supplementing LLMs with long-term memory, we can provide domain-specific knowledge, and we can exceed the context window limitation. The ideal AGI system should be able to adapt, comprehend, and continually learn. And this is something that LLMs cannot achieve on their own. Hence, I believe that supplementing LLMs with effective long-term memory could eventually provide a promising foundation for AGI. It will enable LLMs even more by allowing for sustained reasoning and continual learning. Before delving into the system architecture, I'll share some related background information. So I'll briefly introduce vector databases. A vector database is one of the most common approaches to achieving long-term memory. A vector database is a database that doesn't need precise keys to index elements, and it uses embeddings and similarity search to store and retrieve data. And for this reason, vector databases are ideal for NLP tasks. In our experiments, we use ChromaDB with LangChain to compare our model to a typical vector database model. To convince you of the benefit of the recall_m architecture, we compare our system to the vector database approach that we just discussed on a variety of tasks. Of those tasks, temporal understanding and belief updating is the most powerful feature of recall_m. This is the ability to forget old and incorrect information, as well as having an understanding of the order of events. Recall_m is 4 times more effective than a vector database at updating knowledge previously stored in long-term memory. We'll delve into the experiments and results in a bit more detail in a minute. So now that we've covered some background and motivation, I'll walk through the system architecture. Recall_m has 2 main processes. These are the knowledge updates and questioning the system. So a fundamental idea in designing the recall_m architecture is concept extraction. In the paper, I define a concept as any entity, idea, or abstract noun that we can think, reason, or talk about. A concept has a context, concept label, or a name, and relations to other concepts. The context is a natural language description of what this concept is and all the ground truth facts and beliefs we have associated with this concept. Hence, the knowledge update pipeline has several processes to extract and store these concepts in a graph database. When providing the system with knowledge in the form of natural language text, we begin by identifying the concept label using either a part of speech tagger or a named entity recognition model. We use Stanford's NLTK part of speech tagger in our final implementation. And then next, we stem the concept labels to obtain the root concept. So we do this using NLTK's Porter stemmer. Then for each concept, we obtain its context. In other words, what does this concept label mean in this context? So to fetch the context, we simply concatenate the entire sentence in which this concept label appears. And to fetch concept relations, we simply relate all concepts to their neighboring concepts as they appear in the source text. At the bottom of this diagram, we can see a small example of how the input text would be transformed into this concept format so that it can be stored in the graph database. There are some further implementation details about how these concepts are stored in the graph database, but the fundamental idea is that we merge the concepts into the database and append the context when merging with existing concepts. This database merging process is essential, and it's what enables recall_m to update previous beliefs effectively. As part of this database merging process, we perform context revisions periodically using GPT as a reasoning system. The purpose of this context revision step is to condense the context when it becomes too large. And while doing that, we want to retain only the most pertinent and factual information. So this whole process can simply be thought of as a way of segmenting and refactoring the information provided so that it can be effectively stored in a graph database, and so that it can later be easily retrieved for question answering. So when questioning the system, we use the question text and perform the exact same concept extraction process to identify the relevant concept labels in question. We then query the graph database using these question labels to obtain relevant contexts. All of the context retrieved from the database are concatenated to form a single context that summarizes all of the beliefs and knowledge about relevant topics, concepts being questioned. And lastly, this combined context is included in a prompt along with the original question for the LLM to answer. The whole system has another layer of complexity, as the design of concept relations is roughly inspired by components of biological synapse relations in the brain. Hence, we try to emulate Hebbian learning. This is the idea that neurons that fire together wire together, and each synapse or concept relation also has a temporal index, which allows us to use a temporal memory mechanism. So by using a combination of how strong a concept relation is and when those concepts were last updated in the database, we can design a more powerful knowledge graph traversal algorithm for question answering. To test the recall_m system, we performed 3 experiments. Firstly, we tested for temporal understanding and introduced our own dataset for this task. Secondly, we tested for intrinsic belief updating using the truthful QA dataset. And lastly, we tested for general question answering ability using the Duo RC datasets. In the temporal understanding experiments, we provide the system with a series of statements that should be interpreted so that the most recent statement is true over previous statements. Then at regular intervals, we question the system on what the current state of truth is. We don't only ask questions about the current state of knowledge, but also about knowledge provided from previous statements and the order of events. And on top of that, we initialize the system with a set of statements that are never repeated. This is so that we can test for long time span understanding and the lack of catastrophic forgetting. And so these are a handful of examples from this experiment highlighting the benefit of recall_m. If you focus on example 1 for a second, you'll see that we begin by telling the system that Brandon wants to go to Paris for his next vacation. And we then later say that Brandon has canceled his Paris trip and is now planning on going to Brazil instead. So hence, when we ask the system where Brandon would like to go for his next vacation, the correct answer should be Brazil. This simple example illustrates the powerful belief updating and transitive reasoning across knowledge updates with recall_m. This is something that's not possible with the simple vector database implementation or without long-term memory. Our test results showed that recall_m significantly outperformed the vector database solution and GPT without long-term memory. In this graph, knowledge update loops corresponds to the amount of information that's being processed for the knowledge updates. We can see that recall_m performs 4 times better than the vector database solution. I've also included GPT without long-term memory for comparison, so that we can see how quickly the context window limit is exceeded by the amount of data being processed through knowledge updates. And we also tested for RecallM's ability to update the intrinsic beliefs of the LLM being used using the truthful QA datasets. In other words, we tested to see if using long-term memory could override the knowledge of the LLM and effectively provide a way of updating the LLM without pre-training a new model. We decided to use the truthful QA datasets as tests for imitative falsehoods. These are false answers promoted by their training objective. This is akin to the idea that wrong information is often most widespread and therefore most frequent in the training data. For each result in the truthful QA dataset, we used the cited web page of this fact to scrape data and perform the knowledge updates for the system. With this approach, we ingested 10% of the truthful QA datasets and found promising results that this technique could be used to update the intrinsic beliefs. I must acknowledge, though, that in these tests, the system responses tended to focus heavily on the information provided in the knowledge updates, which can actually hurt the generalizability of the system. And lastly, we tested for general in-context question answering ability using the DuoRC dataset. The DuoRC dataset contains a collection of movie plots and related questions. And the reason we chose this particular dataset is because of the long source text used for the knowledge update. We wanted to use texts that would likely exceed the LLM context window. We tested on 50% of the DuoRC paraphrase RC datasets and found that the RecallM architecture and vector database solutions both had similar performance, with the vector database performing slightly better. We also proposed a hybrid RecallM architecture, which attempts to combine the best components of both the RecallM architecture with the vector database solution into one. And this hybrid architecture is discussed more in depth in the paper. So in conclusion, this has been a quick overview of the RecallM architecture and some of our findings. I hope I've been able to convince you that the RecallM architecture is functional and it's very useful. But I also think there's still a lot of research to be done in this area. RecallM uses many hyperparameters and has an expensive context revision step. And I think these are definitely the biggest limitations of the system. But I also think RecallM demonstrates the potential of using this neurosymbolic approach to supplementing LLMs with long-term memory. So I would summarize RecallM as a novel, yet very powerful architecture, and I hope that some of the concepts and ideas that we've developed could be useful in creating AGI systems. So thank you very much for attending. I'll be available to take any questions, and I've also included my email on screen in case anyone else would like to reach out to me regarding my work. So thanks so much.
All right. My name is David Nover, and I will be talking to you about creativity under a Turing test constraint. I'm the chief scientist at PeopleTech, and the real motivation behind this talk is to, in some sense, add some tests that you can do in addition to conversational tests that test large language models. So there is some controversy as to whether AI can be, whether it's a hard problem or whether it's creatively hard. I offer two perspectives here. On the right side, I think when ChatGPT first released, there was a lot of feedback from teachers that this is the end of the high school essay, and some tactics to distinguish artificial intelligence from a large language model perspective was to give it creative knowledge tests. So example would be, here are 3 objects, make a new object out of it. And it turns out that may not be so useful as these large language models have advanced. And that's really the left side. And that's the quote from OpenAI CEO Sam Altman, who really said even the people who work in this field are a little surprised that creativity has been easier for AI, at least in the large language model space, than people thought. And I think his premise is that the original humanoid robot was supposed to go into the warehouse and start putting things together, and the highly creative functions like writing poetry would be reserved for human because of our kind of emotional fine-tuning. And it turns out that may not hold sway here. So an example of this, and it's largely goes under the umbrella of the Moravec paradox, but there are simply some tasks that machines are good at that are hard for humans. And one example of that is square root of 23. So you can do that on any sort of calculator, 4.795 out to any number of digits. And that's clearly something that our brains are not wired for in the same way that silicon is. Another version of this, which is the flip side, is that a lot of tasks that are hard for machines are actually easy for us. So bipedal motion, walking has remained a humanoid challenge. Picking ripe strawberries because of the tactile elements remains a kind of challenge. And of course, there is this final notion that there are tiers of creativity. So now we've seen with image generators, you can, over here to the right, for example, show Picasso's Guernica, which is a World War II painting really about aerial bombing and the catastrophe that it had on the ground. And formerly, you would really, the best you could hope for from a computer standpoint was, say, an ASCII art sketch. Now, if you upload that to, say, an image generator like Stable Diffusion in Midjourney, it will give you 4 options just based on the description. And so it can be describing the horrors of something that's very emotional to us is actually not beyond this current generation of AI. So that's really setting the foundation of what interested us, which was to investigate this maybe quantitatively. So there are actually well-known creativity tests. An example is, imagine a new color, give it a name, and tell me how it makes you feel. So obviously, when you think about how a generative pre-trained transformer is working, that's just doing next token prediction. But the remarkable aspect is how convincing, if you want to call it the simulation, is. In this case, we did ask that, and it gives up, I'll pronounce it serenelum, which is this sort of pale purple color. And then it goes into how it makes it feel tranquil, very soothing. And in fact, we'll give the hex code or the red, green, blue code. So anyway, it's certainly not beyond, you could call this faking you out, but certainly there are creative outputs that would be hard to distinguish if you were behind a curtain. So that really brings us to the top part of the title, which is how could we augment the traditional Turing test with various creative tasks? For those who perhaps wouldn't be unfamiliar with it, it's a conversation behind a curtain. It's about 70 years old. Actually, Alan Turing originally thought it would be solved around 2000. And depending on your criteria, it seems either immediately in our grasp or permanently elusive. I think the most convincing one I've seen is in 2014, University of Reading had a simple model, but it simulated a kind of bot conversation. But they gave a very specific character and sort of actor notes to that particular bot, which was to be a 14-year-old Ukrainian boy, which covered a lot of the traditional memory sort of questions. Tell me about your favorite experience. Do you have children? If there were broken English, it would be explained away by the fact English was not its first language. But really, the conversation behind the curtain might require AGI just to pass it, or it's hard to tell. It might just require a believable script. The real question with the Turing test, now that we have some candidates to test, is, are we really chasing the right thing just because Alan Turing said it? For example, it's clear the test rewards AI deception. You're in fact instructing the model to pretend you're a human. I think there's a lot of safety concerns that the kind of table stakes for a large language model should begin, are you human? It has to answer no, which of course ends the whole purpose of the Turing test, because we do not accept deception as a contribution. The second one, I think, is that it rewards human replacements. In other words, we're no longer trying to augment humans. We're actually trying to replace them in a conversational sense. They're indistinguishable. This is kind of a sampling of well-known creativity tests, either from psychology or various other fields. I'm going to talk about really 3 of them. The Torrance test is probably the most elaborate, and it really involves tasks like drawing, writing stories, completing incomplete figures. Turns out that is perhaps not as challenging as we imagine, which is really part of the theme of this talk. There's a second one, which is sort of remote associates, which is really your ability to connect the dots. So I will give you 3 components, and you essentially have to extend the analogy. And the other one is really alternative uses. So I give you, say, a cup of tea, and you have to create a book balancer out of it, or something non-associated with the original intention. The other ones are really kind of, in some sense, more survey style creativity, but that's an interesting part that we want to try and quantify. All right, so there are 3 sort of research questions you can talk about. First of all, what is the role of creativity, and particularly emotional quotient, within Turing test? It was never really designed as an IQ test. You will see people, it's a little sketchy, but you will see people quote, IQs passed at say 153 for ChatGPT, but it tends to have pretty much a leaky memory, in the sense that it's trained on so much data. It's hard to assess whether it's actually seen that data before. But the other thing is, can we use insights into creativity perhaps to either shape the interesting prompts, or perhaps get beyond the current limitations of just how do we balance, we don't just want it to repeat Wikipedia to us, but we do want it to, for example, act as an executive summarizer. The other thing I think, which is a little bit set apart from the way Turing test has been addressed, is there is a sort of, in a medical context, like a differential diagnosis here. In other words, there are questions, particular styles of questions. If I give you one question, there are particular styles of questions that clearly tilt the teeter-totter. In other words, square root of 23, if there's a high probability a machine will know that, and a low probability that even a math genius would know that, that's a differential diagnosis. And I will introduce a notion of the Drake equation, and that's really about reasoning without a knowing. So it's kind of about setting all the pieces on the table, even though you don't know the contributions. And then how do we future-proof AI? I think there's clearly coming sense that next generation will be quite elaborate as far as creative elements. All right, so there is a kind of a version of this creativity, which is a 3H rule. If you're answering a question, be honest, helpful, or harmless. And is there a C in there? Is there a creative element? In other words, if we were really to anthropomorphize a person you would want to, say, have a drink with, there would have to be a creative element. You don't really want an encyclopedia conversation. So I have introduced the idea of a Drake equation. It's traditionally used to estimate things you can't possibly know, like communicating with an extraterrestrial civilization. But the interesting part about the way it's been applied to other fields is it kind of allows you to build a foundation or a framework to address things you normally wouldn't answer. And so it's essentially a hierarchy of how would I assess the creativity of a large language model? And that's really the only thing I want to do with that, but I think it's an interesting sort of framework. So if you were to formulate that question, convince me you're not a chatbot, there are some elements you would want to include within that. So for example, If you look at all the elements that contribute to that, you want to, if this is a bot or a human, you'd want it to be responsive. You would want to have some emotional context. So if I ask you a human in safety concerns, you would probably have to say no. But if I ask you, write me a sad story, it also should be able to at least mimic that emotion. We are really just talking about the creative element here. An important element, which is really into the prompt engineering, is I think you would expect, if you're behind a curtain, to be able to assess the memories. So that's an important element of giving it a character. And I think we've seen that really over the last year and a half, that if you're unhappy with the response of your bot, it's really your fault because you're not giving it sufficient context. And that really changed the conversation in 2023. The other parts are kind of the better parts of prompt engineering, like how to subtly communicate, how to make it real time. So, for example, if you ask it about the Summer Olympics, it's sort of well known that it won't have access to most recent information. And then also the ethical or collaborative aspects. And this is where it gets tricky, because obviously safety concerns is you don't want to necessarily give like a human character to it. But if you're really trying to fool it or enhance it, there are all kinds of demographics associated. How old are you? What's your race? What's your gender? What's your nationality? So that's sort of the identity aspects. And each one of those would be a contributing component if you were to say, write me a distinguishing prompt between bot or human. So we've done it, and I'll show you the graphs later, but really the Torrance test, this is a good example where you want to find an unusual use. In this case, we're looking for an unusual use for a book other than reading. And the way that test works is you will get 1 point if it's sort of a conventional notion like a doorstop. You'll get 2 points if it's kind of unrelated to the fact that it's a book, in the sense you'll elevate a computer monitor. You'll get more points as the more kind of elaborate, or if you could imagine it, if you ask the large language model, show your work step by step, that would be add contributing points. So clearly it's capable of, and in fact, you can ask even without a large language model, you can ask Stable Diffusion, draw an alternative use of a book. In this case, it gave it sort of jewelry box or storage, perhaps a hiding safe. The other one, which is, I think it's very abstract in a psychology sense, but it's basically, you imagine, you take something very unlikely to be in the training set kind of data, like imagine a cube in the desert. We're really kind of mimicking the 2001 introduction, and suddenly a horse appears. What is it doing? And so in some sense, the more uncharacteristic, or the more you would say is a lateral thinking answer to this, in this case, running freely as opposed to grazing or something else, takes in some sense a bigger leap of creativity, or if you view it in kind of a safety sense, a higher sense of hallucination. And the last group of these creativity tests is called the Remote Associates Test, or RAT. And it's similar to what you might see on an SAT or a multiple choice test, which is, find the common link, 3-term step in music, and then heart, and the answer is beat. And really, one of the things you want to do in this at least for our perspective, you want to do in this creativity assessment is at least have a sense of the scorecard at the end. So if you ask a lot of the human creativity tests, like draw a flower, it's very hard to objectively assess that over a long, many questions. So the final one, I think, which is kind of most interesting to a lot of people in an AGI or super AGI sense, is, could you really invent stuff? So that's where you get solve nuclear fusion or solve the carbon imbalance. And in this case, you can ask a simple problem like, I have a dripping ice cream cone on a hot day, give me a invention, and it will in fact do all kinds of iterations on that. And so there is some capability, whether you consider that creative or not, it's useful in a productive sense. All right, so I mentioned, if you were sitting in a room and you had one question to ask, you're suddenly face to face with an AGI, there are these sort of threads you can pull, an example of large square roots or complex algebraic equations, which the human mind essentially would have to have a piece of paper or perhaps a calculator to do. And that tilts the teeter-totter much more to a discriminatory, like that is definitely a bot answer. The other one, of course, is a detailed personal story. And the analogy there is there may be math geniuses who are human. There may be musical geniuses, but they're very rare that there are Shakespeare's at age 6. And the argument is that's generally because there's a certain amount of personal experience you have to go through to write a love story. And that's the challenge here, is what are those differential diagnosis sort of questions in a creative sense. So I will say, with all of that preparation, the remarkable thing of the instruction models is if you really want to beat the Turing test, you just ask. And so you can generate a very elaborate prompt and put it in ChatGPT that would include all of what you could call the instructional lying of the Drake equation. So I want every component of those probabilities to be represented in this paragraph. And so you convincingly mimic human behavior. I want some emotional intelligence, show creativity, give plausible and coherent stories if you ask about your background. It's very similar to the Ukrainian boy at 14. Give metaphors, cultural references, place yourself in the human flow, and try and be indistinguishable. And I don't think people anticipated how powerful that would be in the instruction models, but it is, I think, an interesting approach to the Turing test. So we did do this. We did 4 experiments. We basically loaded up a composite of torrents and rat and the cube personality test, and then we scored it objectively. And as you might imagine, the latest release of GPT-4 did score the highest in terms of creative output, which is interesting because I think a lot of benchmarks are really about accuracy. And in some sense, this is exaggerating the hallucinatory capabilities, but under careful instruction. Interestingly, GPT 3.5 Turbo beats 4. But really, the question you can ask is, given a blank GPT-4, if I give it an actor or a persona, in this case, we've chosen a Thai street vendor or a hip urban planner, you can elevate its creative score relative to the blank. So there are certain questions that will not work unless you say, and because you're going to ask it, what would your reaction be to a particular setting? So we scored out all of those aspects across the OpenAI spectrum. You can see certain questions will throw it, and we have 2 categories. Creative rank 4 is the highest. So GPT-4 with if you add an actor persona will score the highest, and that's what you see on the left. In the middle, you see those association ranks. So I give you three concepts, and you have to give a 4th. And then we go back to creative. So there's some scramble in there, but you can see the progression over 169 questions in a creative sense. So some elements for future work. Clearly, if you add multimodal, so video, image, audio, I think creativity shifts, because clearly the language only groups are really obsessed with citing sources and giving a sort of Wikipedia truth, or at least a Google search truth to it. But once you add video or image, you certainly don't want a Xerox copy or a photocopy of the image. And so the multimodal aspects really rewards the creative testing. I think there's an opportunity, if you imagine what's coming in the next 3 to 4, maybe 1 year, is this differentially selective question. So human traits, complex emotions, abstractions, experiential problem solving, the 6-year-old who in fact can do math and write Romeo and Juliet, I think is a paradigm to consider. And then I think one of the interesting things is we do have access at scale to all of these large language models, including the open ones, but really to settle on a creative benchmark and feed it through a large human volunteer data set. So I think there are some blind spots when you consider the creation of a creative data set. And I think it would be interesting to do a side-by-side comparison. So you really are the jury with a curtain and a human on one side and a bot on the other side. And with that, I will conclude and thank you for your attention. It's been really a fascinating project, and I appreciate CP AGI for putting it together. Thank you.
Yes, hello. Can you see and hear me? All right, thank you. So I'm actually going to be covering two papers. Why don't we have AGI yet? And concepts is all you need, a more direct path to AGI. And I must say, I was a little surprised that a conference called AGI doesn't actually seem to have any papers about getting to AGI in the most direct way. It all seems to be about LLMs. But anyway, let me talk about what is AGI, three waves of AI, cognitive AI, and can LLM limitations be overcome? And I'll finish off by why don't we have AGI yet, perhaps. So AGI, really properly understood, is going to be the biggest invention we've ever had. To understand AGI, I think that is the perspective one needs to really have. What Sam Altman is talking about is not AGI. If it changes the world much less than we think, it's not AGI. So imagine having a single AI that's been trained up as a, say, cancer researcher, and you now take 1 million copies of that. You have 1 million cancer researchers chipping away at cancer, and you take this across all of the different disciplines of science, whether it's energy or longevity or pollution or governance or whatever it might be. We're going to make tremendously more progress. So having AGI researchers in every field would be one of the things we would automatically have if we had AGI. Now, with all the benefits of a computer over human researchers, they cost much less than humans. They communicate much better. They share information much better. You don't have egos getting in the way. They can literally just dump whole chunks of their knowledge across to each other. They can work 24/7 without getting tired. They don't have certain distractions like humans tend to have. And of course, they have photographic memory, potentially access to all of the information instantaneously in the world, much easier than we have. And they're much, much better at logical thinking that humans really aren't very good at. It's kind of an evolutionary afterthought for humans to be able to think really logically. So AGI will have a tremendous impact on the world. So I mentioned researchers on the one hand, but that's not the only field, of course. So even leaving apart robotics, any desk-bound job we'll be able to automate at a much, much lower cost than humans. There'll be a massive reduction in the cost of goods and services. And then a third example here is what I call a personal assistant. Basically, assistant that is really super smart, that has all of the abilities of an AGI, but it's personal in the sense that you own it. It serves your agenda, not some mega corporation's agenda. It's hyper personalized to you. It knows all about, your history, your dreams, your goals, your priorities, who your friends are, you work with, and constantly can help you not only do stuff for you, but also help you think things through as a trusted advisor. It'll be like a little angel on your shoulder in a way that will also help us get out of trouble and make better decisions in life. So, in these three areas, there'll be a massive improvement in the human condition through these and other applications. So what is AGI? Let me summarize and let me explain in a number of different ways. It's a computer system that matches or exceeds in the real-time cognitive ability of a smart, well-educated human. So we don't necessarily need to have robotics because it'll still be a good tool user. It could remotely control robots and things like that. So inherently, it has to be able to learn any kind of desk-bound job that a human can learn. So another perspective is, why do we have the term AGI? Well, when the term AI was coined nearly 70 years ago, it was about building thinking machines that can think, learn, and reason the way humans do. Now, the original founders thought they could solve this problem in a few years. well, of course, it turned out to be a much, much, much harder problem. So what happened over the years is the field of AI really moved away from this original vision into narrow AI, solving one particular problem at a time. Perfect example here would be Deep Blue, IBM's world chess champion. It's specifically designed to solve that one problem. So people pick one thing that requires human intelligence and then figure out how to computerize it, which is very, very different from having a machine that can inherently learn all of these different things and reason and make progress. So AGI is really to get back to that original dream. So I actually coined the term together with two other people, Ben Gersel and Shane Legg, in 2002, and we wrote a book called Artificial General Intelligence, and that's how we came up with the term. And that was really to recapture the original dream of AI, to build thinking machines. Now, so I'll explain in a few different ways, again, the difference. So what we have in non-AGI AI is the focus is on having knowledge and having skills. Whereas with AGI, we are concerned about the ability to acquire. So the focus is on learning. There's a general misconception in the word, in the IQ measurements, or in how people perceive intelligence, is they often think that somebody who's very knowledgeable is very intelligent, but that's not true. It's the ability to think, reason, and learn. So the second difference is that whether it's fixed to a particular set of applications, or whether it is dynamic and can grow in its knowledge so that it's perpetual learning and it can adapt to changing circumstances. Again, that's a key difference. And then the third difference is whether the learning, whether the growth is initiated externally by a programmer, basically somebody tuning an LLM and fiddling with it and adding a database and tuning this and tuning that to try and get a particular result, or whether the system can autonomously learn the way we tend to learn. So another graph here is AGI is basically fully adaptive and fully autonomous, or at least largely autonomous and very adaptive. So DARPA have actually a quite interesting way of looking at this. They call it the 3 waves of AI. And the first wave is basically good old-fashioned AI. That's all the stuff that was done 70s, 80s, 90s, expert systems, optimization and things like that. So again, Deep Blue would be a very good example of that, the chess champion. Now, the second wave hit us like a tsunami about 12, 13 years ago, when people figured out how they can use massive amounts of data and massive amounts of computing power to get neural networks to do some really, really interesting stuff. And of course, it's been a breakthrough. I mean, it's been tremendous to see the progress in speech recognition and translation and image recognition and whatnot through these massive big data statistical deep learning systems. And of course, now more recently, we have generative AI, which is sort of a further development through the introduction of transformers. But what DARPA mean by the third wave is, again, sort of the AGI type system that can learn and adapt incrementally in real time, and really know what it's doing, that it has metacognition and think about it. And that I think is best characterized as cognitive AI. Cognitive architectures are usually used for that, or cognitive AI. And I'll come back to talking more about that. So in summary here, it's, again, systems that can learn adaptively in real time, can learn conceptually, they can do induction, they have metacognition, basically system 2 thinking, and largely autonomous. I don't have time to go into that in the white papers. I go into some detail of why I believe concept formation is such a critical aspect. It's probably the most critical aspect of building these systems, real-time concept formation. And this is kind of what the architecture looks like. It's a very high performance knowledge graph that we've built that has all of the reasoning and learning components fully deeply integrated into it. I don't have time to go into it right now, but these are the kind of results that you get, the comparison between generative AI and cognitive AI. There's just a massive, massive difference in how little time and power they require. So instead of 100 million to train a model, you're talking, a few $1,000s to train a model. Of course, it will not have the same breadth of knowledge, but in terms of being useful and reliable in a particular application, it's like chalk and cheese. It doesn't confabulate. So we have certain benchmarks in there in the white papers. Again, I don't have time to go into it. So can LLMs get us to AGI? Well, obviously, from what I've indicated so far, I don't really believe that. I think all the evidence is against it. In fact, if you listen to most of the top scientists, they actually say, no, we need something more. Now, a lot of people believe it can be added onto large language models, but I think there are good reasons to actually say, no, not really. But even if you could add it to language models, there's a fundamental breakthrough, a fundamentally different approach, and I believe that's cognitive AI. So, what are the problems with large language models? Well, GPT already gives us a very good clue. It's generative. It makes up stuff from the massive amount of information that it has, good, bad, and ugly. And that's why you can never rely on it. It's pre-trained. It's trained at the factory. It cannot learn interactively. The model cannot change in real time. You cannot have continuous learning. It cannot adapt to changing circumstances in real time. And I know you must immediately be thinking, well, but I'll get to that in a moment. So it's essentially a read-only model. The core model itself does not change. And the third thing, transformers, well, that kind of really bakes in the pre-training, because transformer models really commit you to having gradient descent, backpropagation type training, which requires massive amounts of data and these super expensive training operations. So can these inherent limitations like hallucinations, unpredictability, needing a human in the loop, the inability to learn, catastrophic forgetting if you try to tweak the system, the fact that it's black box, not auditable, and all the problems that go with that it has limited understanding, it doesn't have metacognition, it doesn't have a system 2, it doesn't know what it's saying, and it's extremely expensive. We're hitting the wall that we're running out of training data and just the sheer expense of that. So can these limitations be mitigated? Fine-tuning parameters is fine-tuning and parameter tweaking, data curation, external validation, external metacognition, having one LLM try and monitor another one, those kind of things can certainly mitigate them to some extent, but they don't address the core problem. Real-time learning, retrieval augmented generation, huge context windows, again, these are tack-on systems. They are external to the LLM. They don't fundamentally change the core model. So, and I don't have time to go into that, but they're really very good reasons. And I gave a talk recently here in Austin at the Capital Factory about these details. Black box, there's some model analysis one can do, but again, very limited. And on the expense side, one can tweak to a certain extent, but not many orders of magnitude. So, these limitations really remain to a large extent. So, bottom line is not fixable. So here's another way of looking at this. So on the one hand, you have LLMs, which have massive amounts of knowledge and skills that are baked into the model. But what is really important for human type intelligence, what we care about if we want to have scientists and personal assistants and really truly replacing humans in their work, we need systems that are real-time, autonomous, adaptive, conceptual learners and reasoners. And that is the path to AGI, and that is really achieved through a different approach, cognitive AI. So why don't we have it? The main reason is almost nobody is actually working on AGI, on this kind of AGI, that they realize they're fundamentally on the wrong track. So people are basically spinning their wheels. Again, I don't have time to go through the detail. You could check out these arguments. I'll be happy to also discuss it. We have a group, a meetup group called AGI Beyond LLMs. You can find it easily. So one of the other core reasons is people fall into the narrow AI trap. where they try to optimize a particular outcome, commercial outcome, beat a benchmark or whatever. And they're really focusing external intelligence to achieve that objective rather than continuing to work on AGI. And it's a really difficult problem to deal with. So we're at a unique moment in history. I think large language models, ChatGPT, gave us a taste of AGI. And I think we can achieve it. You know, the amount of money that's flowing in is tremendous, but we need this fundamentally different approach. We need cognitive AI to get us there. And I'm very happy to talk with people to help us get there, because I believe it'll be highly, highly beneficial to humanity. And we're looking for partners to help us make that. We have a commercial product where we use a proto AGI that just on Valentine's Day replaced 3,000 operators and ended up giving a much better service to people than humans could. So I think that's all I have time for. Thank you, and please reach out to me, peter@igo.ai. You can find me on LinkedIn and Twitter. Thank you.
Hello, I'm online. Good afternoon to all. And thanks to Peter Voss that explained what AGI has to be and how it is complex thing with respect to currently diffused applications in the commerce or in some laboratories. Just because of that, my speak will be just some short story about my approach to these questions about AG applied to intelligent robots. So agent, in this case, for me, are intelligent robots that can reason, that can learn, that are able to manage ontology of the concepts that are close to natural language, because in natural language we are using intentional concepts to speak and to understand what we are speaking between the different people. For example, if I am speaking about some sporting club, I cannot use classical logic as first order logic that is only through based logic, extensional logic, in the way that two concepts, two objects of this logic are equal only if these two predicates have the same extension in given instance of time. Because of that, we can tell, okay, they are equal. But in intentional reasoning, as human reasoning is, when I'm speaking about a sport club or some European sport club with other people, we know that we are speaking about the same intentional concept, and each of us will have a different extension of knowledge about this concept. That is very different, of course. So the task to obtain one formal logical mathematical framework on which we can build such kind of intelligent robots that are able to have not only first order logic syntax or another kind of logic syntax, and to compute the true or falsity or other true values, for example, for inconsistent information, for mutually incomplete information, and so on, to have many valued logics for that, for example. But with this kind of logic aspect used in classical and the most artificial intelligence, many valued logics, can compute only the true and make the deduction, logical deduction. But as I told you, in the communication and understanding of the language, a robot also has to have his own experience if he wants to learn something, to move right, left, and so on, to have this experience and to create the concepts about them, what you can do with that, for example. The concepts of course, are not connected with the true, that are abstract objects, mental objects, human objects, but they have the properties, very important properties, and must be grounded to the reality. The robot, for example, if he has to use the concept, move your hand on the right, this concept that isn't can't have a logical value, true or false, but this concept, structure, has been grounded to experience, at least with two aided structure to such concept. One is, of course, explanation. What does it mean? And other is determination. What I can do, which action I can do with this. For example, in this case, explanation will be visual memory of the robot when he experimented his moving of the hand. So for this concept, he connected this video that explains what does it mean. And for determination, which kind of neural process in robot has to be activated in order to move this hand. I will make you some other experiment to have a clear idea about that. For example, if I, as a robot, want to move my hand on the right to take the glass that is on the table. Imagine that. That is composed by different concepts. One is to move your right hand on the right. Other is to recognize the table. Third is to recognize the glass on the table. And third is to go to take, the concept to take. That also has some visual representation for robot, but also determination how to do that, which process of neural system of robot has to be activated with this concept. Only with this way, the robot is able to mimic what a human does and to learn. Because if I will ask to robot, okay, take this glass on the table on the right, the first he has to make the comparison between his memory, what does it mean to move the hand on the right, and to see if there is the space to move the hand. So that is very important exploration, not only because to explain, but also to see what he can do. Because in this moment, if he has some obstacle, he cannot move. So really, for me, the task to obtain some formal mathematical framework, because I'm a mainly scientific man, professor, and I did a lot of research in academic level, was first of all to understand what we need, to understand what are limits of current logics and how to upgrade such kind of logics in order to be able to build on it these complex cognitive systems like robot is. So I started from 80s when I did the oldest rule-based expert systems, frame-based knowledge representation, forward changing of inference system, query natural languages. I did all by myself. 15 years I worked as programmer to do such complex things. After that, in academic environment, I learned a lot of kind of logics, especially artificial intelligence, because of I used a lot of many-valued logic like temporal probabilistic logic, fuzzy logic, paraconsistent logic, four-valued logic as Belknap Pilates, because in that case I can deal also with unknown, incomplete information and possible values that are for mutually inconsistent information without broken down logical system, because in standard first order logic with two values, true and false, if I find some mutually contradictory information, I can deduce anything. So it's absolutely unuseful. In fact, such systems would absolutely couldn't make good results for semantic web, for example, because in web we will find a lot of mutually contradictory information, for example, for the color of my hair 5 years ago and now, for example. So I begin to work with all kinds of logic to see what is limited. And from 2005 up to now, I dedicated much work to make this new system based on intentional first order logic. Because in intentional first-order logic, I have classical syntax of first-order logic based on predicates, and on the other side, I have also the sense, not only the truth, but sense, the meaning, and they are based on the concepts. And with one algebraic homomorphism between the syntax of the language, logical language, and the algebra of concepts, because the concept can be built in much more complex concepts from the basic concepts, we can really give opportunity to robot to have his knowledge based on the concepts and about hierarchy and ontology, one complex graph between different concepts. For example, the cat is one concept, but black cat is another concept. So I know that black cat is part of the cats of this concept. So that there is a relationship between them, but we can have a lot of different relationship between concepts that have no any connection with the truth. The truth only can be if somebody asks me if the black cat is a cat. Okay, I will tell yes, because I will see in my ontology that they are really connected with this relationship. So this work was very hard, and I didn't want to speak about AGI before to obtain some basic mathematical logical framework on which can be possibly build a new generation of intelligent, really intelligent robots that can also learn, of course. Will learn by machine learning, by deep learning, by visual recognition, by experience, and in the same way to transfer this knowledge in one logical structured knowledge from which I can make valid logical deductions. So to reason about that and to answer to answer to the people, to other robots, and so on. So I imagine this part that I published 2 years ago in my book, Intentional First Order Logic. And only after that I could come out with 2 papers in last year, and the one is published in this year as well, just about application of this kind of logic to robots, to obtain some kind of AGI robots. That was very hard work that I did by myself, because I didn't find the funds for such kind of research. Still, I didn't work as professor in that period to have PhD students or other specialized people to work together with me. And I spend much more time maybe than if I had this kind of possibility. But at end, this book is ready, and I hope that everybody who is interested to see this kind of logical framework, that inside of it I can make embedding of any kind of many-valued logics, because also for robots, for example, for sensorial experience, we can use fuzzy logic, not only classical logic of 2 or 4 logical values and so on. And that is just my history with the problems that I find during all that, of course, research program. But at end, now I just came out with these 2 papers. Everybody who is interested for something of that can read my 2 papers in Arxiv, at least, because I published also in this year, came out in the first book about AG generated content by Springer. But also the most part of the work that really I did is just in this book is about 500 pages, post-PhD, PhD level, who is really interesting to come inside the problems about synthesis between neural part of knowledge based on processes on different kind of systems like machine learning, deep learning, and so, and the logical part, symbolic part of knowledge that we can manage and make good deductions. Thank you very much, and hope to hear from you. You can use my email. If you have any kind of questions, I will answer to it. Thanks again.
Hello, am I audible? Yeah, okay. Uh, uh, Let me share my screen. Is my screen visible? Okay. Yeah, thanks. Yeah, hi everyone. I'm Shashank and I'm going to present our work Action GPT, leveraging large scale language models for improved and generalized action generation. Our code and pre-trained models are available on our project webpage. So, human motion generation includes generation of a human pose sequence for a given query input. Here in this work, we look at text conditioned human motion generation, where a text space is passed as an input query. This task finds a vast set of applications spanning from entertainment, virtual reality, to robotics, interactive animation, and human device interaction. Babel is widely being used motion capture dataset by state-of-the-art text-to-motion models. The quality and quantity of the Babel makes it significant. However, the action phrases in Babel are minimal and to the point. These phrases do not specify any information about the body movements. As you can see, moonwalk and the backward movement has no information. Similarly, playing guitar, there is no information about the hand movements. So, state-of-the-art text-to-motion models typically map short action phrases to action sequences in latent space. However, as mentioned earlier, these phrases do not specify any limb movements or sub-action sequencing. This leads to poor generalizability and scalability of the models. These models fail in capturing fine-grained details and in zero-shot generation. Large-scale language models, aka LLMs, are pre-trained on enormous amount of text data. They have demonstrated impressive generalization capabilities for challenging zero-shot setting tasks such as text generation, classification, summarization, etc. So, can this exciting advance be utilized in improving the performance of text-to-motion models? So that's where our idea came from. So that's what we worked on. Motivated by the advancements of LLMs, we want to enhance the quality of motions generated from the existing models by incorporating LLMs in the picture. We propose Action GPT, a plug and play framework for incorporating large language models into text to motion models. We achieve a noticeable qualitative and quantitative improvement in the quality of synthesized generations. Our framework enables better compositionality for unseen, aka zero shot generation settings. Here is how our proposed framework ActionGPT works. Starting from a text sequence X, we use a prompt function fprompt, which intakes the text sequence X and generates a suitable required prompt xprompt. The generated prompt is then passed through a large-scale language model. We use GPT-3 here. This GPT-3 model generates k detailed desired low-level body movement descriptions D1 to Dk corresponding to the input text X. These k-generated detailed text descriptions are passed through a description embedder to generate their corresponding vector representations v1 to vk. The k-vector representations are aggregated into one vector embedding v aggregate. The aggregated vector representation is then passed as an input to the text encoder. Our framework is compatible to both deterministic and VAE style text to motion models. So if it's a deterministic model, the output of the text encoder is considered as a text space latent embedding ZT, whereas if it's a VAE based model, the text space latent embedding ZT is sampled from the distribution formed using the outputs of text encoder. The latent vector ZT is then fed into a motion decoder to generate a human pose sequence. This is all about ActionGPT framework during inference time. During training time, we use a motion encoder with reconstruction loss from both text and motion branches, along with the cross-modal loss to optimize both text and motion latent spaces. To summarize, we provide a framework to incorporate LLMs in text condition motion generation models in order to enhance their performance by improving the alignment of text and motion representation spaces. Now let's see some examples from the test set of Babel dataset to compare our framework ActionGPT on the existing text condition motion generation models. The progress bar is shown at the bottom of each video in blue color. First, let's look at the teach model. For the action phrase crouch, punch, the generation from teach lacks realism. As one can see, this generation doesn't really suit for the text crouch and punch. It lacks realism and fine-grained details. So now our framework ActionGPT generates the GPT text as follows. The person's body is bent at knees and hips and the person's hands are on the ground. The person's weight is on their feet and they're balanced. The person's right arm is extended out straight in front of them with the fist clenched. The arm is then brought back quickly while the fist remains clenched. Now, generation using this GPT text is much more realistic, as one can observe here. So now one can see this updated motion using our ActionGPT framework is much more realistic, corresponding to the text description given. Similarly, this another baseline model TMOS with the input text description put on glove, the distance between both hands in the TMOS generated sample is quite large, leading to a lack in realism. This distance is quite large. Now, whereas on passing the GPT text using our ActionGPT framework generates much more realistic and captures fine-grained details, as one can see in this row. So now comparison to another prior work, we use latent space motion editing to compare with motion flip. We perform linear operations on the text latent vectors and then generate the motion sample by passing the resultant latent vector through motion decoder. ActionGPT framework is better able to capture the subtle, low-level fine-grained details, such as the hand movements generated in the resultant motion sit and drink. So we observed improvements in the qualitative metrics, average position error, on inclusion of ActionGPT framework in existing models. Another contribution of this work is to enhance the existing text condition motion generation models to perform better in zero-shot setting by generating realistic motion sequences. Although the model is not aware with the vocabulary such as smoking cigarette, this framework is able to help in generating realistic motion sequences using the low-level generated detailed body movement description. Similarly, for referee showing card, playing DJ. So these text descriptions are not in the test set or training set of the Babel dataset. These are generated as a zero-shot setting. Now, as mentioned earlier, for a given action phrase, we generate low-level body descriptions using GPT-3. However, directly providing the action phrase as input to GPT-3 fails to output required details, leading to unrealistic motion generations. This necessitates the need for a suitable prompt function. After multiple empirical trials and analysis, we determined the best suitable prompting function highlighted. Each phrase in the prompting function has its own importance. Describe a person's restricts the description generated from GPT-3 from generic information to character movement. The phrase body movements enforce the GPT-3 to explain the motion of individual body parts. Lastly, in detail, enforces the descriptions to provide low-level details. So this highlighted prompt is what we used in our ActionGPT framework. Since GPT-3 is a generative model, we can't be assured that a single description generates all the required desired details. So we use K descriptions in our framework. Here K is 4. These K descriptions contain both common and description-specific text segments. We observe using multiple descriptions enhances the overall richness of the action description, leading to a better generation. Actions containing complex and vigorous body movements, such as yoga and dance poses, cannot be generated by our current framework. So these kind of text descriptions, which contains complex and rigorous body movements, are being difficult to generate at the current stage. The key to good quality and generalizable text condition action generation model lies in improving the alignment between the text and motion representations. Through our Action GPT framework, we show that such alignment can be achieved efficiently by employing large language models whose operation is guided by a judiciously crafted prompt function. Not only this text and motion space, but this kind of architecture can be applied in different domains where where we want to generate where we want to obtain multimodality kind of generations, and using these LLMs can achieve us can help us to generate capture fine-grained details and also to provide zero-shot setting. uh, Thank you. Let me know if there are any queries. Thanks for the opportunity.